that feeling when you look at a massive block of dense math equations and you feel like you're staring at a locked safe with absolutely zero idea what the combination is? When variables, coefficients, and equations start piling up, it's so easy to get completely overwhelmed by all that visual noise. But what if I told you that beneath all of that chaos, there is a beautifully simple, deeply satisfying mechanical process to unlock it? It's honestly just like cracking a code. All we need is the exact right sequence of moves to get those tumblers to click into place.
Welcome. I'm so excited to guide you through this explainer today. We are going to take intimidating fractions and grids and turn them into some truly satisfying discoveries as we step into the world of matrix mathematics and linear systems. By the end of this, you aren't just going to see grids of numbers. You'll actually see the exact levers and dials you need to pull to bend these equations completely to your will.
So, here is our roadmap for today. First, defining linear equations. Second, matrix row operations. Third, solving complex systems. And finally, visualizing the solutions. All right, let's just into Section 1, defining linear equations, spotting the patterns. Okay, first things first. We have to recognize that not every math problem is actually a candidate for our matrix toolbox. We really have to spot pure linear equations. You see, equations involving plain variables like x1, x2, and x3 represent clean linearity. That's just variables standing entirely on their own, multiplied by constants. But if you start seeing variables with exponents like x squared, or variables trapped inside trigonometric noise like cosine, or even variables multiplying with each other, well, those aren't linear. They create curved, bent, and wavy lines in space. And we are strictly looking for the straight and narrow path.
Moving right along to Section 2, matrix row operations, the tools of the trade.
Think of these as our authorized keypad inputs that let us safely decrypt the matrix step by step. They're called elementary row operations, and we only have 3 of them. First, you can swap any 2 rows. Second, you can multiply a row by any non-zero number. Or third, you can add a multiple of one row to another row. That is literally it. As long as you stick strictly to those 3 rules, you will never alter the true solution of the system. You're simply changing its appearance to make it much easier to read. And this is a brilliant illustration of the bridge from traditional algebra over to linear algebra. We take traditional equations, we literally drop the variables, strip away the equal signs, and just encapsulate the raw data, the coefficients and the constants, into a nice, neat, bracketed grid, a matrix. Here, we're taking the second row and scaling it by multiplying it by 1/2. Notice how much cleaner everything looks when you can just focus purely on the numbers.
So here is our conceptual map. This is our algorithmic master plan, designed to keep you from getting lost when those numbers inevitably start turning a little chaotic. Step 1. In your current column, get a leading 1. Step 2. Use that 1 to clear out all the numbers in the column directly below it, turning them into zeros. Step 3. Shift down and to the right. And just repeat the process. We are systematically building a perfect staircase of 1s right down the matrix. Let's put this into practice in Section 3, solving complex systems, cracking the safe. We almost always start with a messy reality, right? 3 variables, 3 equations, x1, x2, x3. We've got negatives, positives, coefficients scattered everywhere. It looks totally daunting. But remember, we are not going to panic. We're just going to systematically follow our code-breaking steps. We drop those variables and translate this directly into our starting matrix. Now, we want a leading 1 in that top left corner. Sure, we could divide the entire first row by -3, but that's going to create some really ugly fractions right out of the gate. So let's work smarter, not harder. Take a look at the second row. It already starts with a 1. So our very first authorized move is just a simple row swap. We exchange row 1 and row 2, boom. We easily snag that crucial leading 1 at the very top left, no fractions required. Now, this is where it gets really interesting. We can actually use that top row as a sort of weapon. We have our leading 1, and now we need to zero out the -3 and a 2 sitting just below it in the first column. To kill a -3, well, we need a +3. So we multiply row 1 by 3 and add it to row 2. To kill the +2, we just multiply row 1 by -2 and add it to row 3. Just look at that beautiful first column, a solid 1 at the top and clean zeros below it. The path is clearing. Now, I'll admit, the arithmetic and the middle and right columns might be starting to look a little intimidating right about now. We've got 8s and 5s popping up, but just trust the process.
Step 1 is done for the first column. So we shift our focus down and to the right, landing on the middle entry of the second row.
Okay, we need that middle 2 to become a 1. How do we do that? Super simple. We just multiply that entire second row by 1/2. By doing this, we effortlessly create our next leading 1 in the second column. Click. The next tumbler falls into place. Sticking faithfully to our master system, we now use that brand new anchor point, our leading 1 in the second row, to wipe out the number directly below it. We've got a -3 sitting down there. So we multiply our second row by 3, add it to the third row, and boom, it becomes a 0. We are almost entirely through the lock now. We shift down and write one last time. There's a 5 sitting in the bottom right corner of our variables. So we scale that final row, multiplying it by 1/5, to reveal a clean leading 1. Notice that beautiful diagonal staircase of 1s with a perfect triangle of 0s right beneath that? This state is called row echelon form. But we want to go all the way. So for a highly satisfying final sweep, we actually work in reverse. We use our leading 1s to clear the numbers upwards. We use row 3 to zero out the numbers above it in column 3. Then we use row 2 to zero out the number above it in column 2. And this leaves us with nothing but a perfect diagonal line of 1s and 0s everywhere else on the left side. This ultimate, completely clean state is known as reduced row echelon form.
And suddenly, out of the chaos of all those initial messy calculations, our matrix collapses into this remarkably clean, beautiful, decrypted solution. The first column is x1, the second is x2, the third is x3. Because of our diagonal of 1s, the matrix is literally screaming the answers at us. x1 equals -2, x2 equals 1, x3 equals 1. We completely cracked it. It's profoundly satisfying to watch those numbers fall perfectly into line, isn't it? But we have to pivot here for just a second. We've done a whole lot of pure computation, purely manipulating symbols on a page. But what do these numbers actually mean in the real world? Like, what did we just find when we confidently declared x1 is -2, x2 is 1, and x3 is 1?
That brings us to section 4, visualizing the solutions, geometry of the code. So here is the absolutely crucial point. Cracking this matrix actually means finding the exact physical coordinate where multiple lines or planes perfectly collide in space. Every single linear equation represents a straight line, or, if you're in higher dimensions, a totally flat plane. When we solve a system, we are asking a highly precise geometric question. At what exact coordinate do all these flat surfaces intercept at the exact same time? But we have to remember that our universe isn't always so neat and tidy. Sometimes we get a single perfect point of intersection, exactly like the -2, 1, 1 we just found. But geometry has other possibilities, right? Sometimes planes run totally parallel. Think of the floor and the ceiling of a room. They are never, ever going to touch. In matrix math, that physical reality translates to a system with 0 solutions. Or, consider this. What if the equations actually represent the exact same plane lying perfectly on top of itself? As our source material highlights, sometimes our matrix won't give us one single solitary point. If those planes perfectly overlap, or if they intersect along an endless line rather than a single dot, we get infinitely many solutions. And in those cases, a single matrix column vector just isn't going to cut it. We have to use parametric equations to describe an infinite, overlapping reality. Basically, our matrix tells us the structural relationship of the infinity, rather than giving us a single locked-in destination. Which leaves us with this final kind of mind-bending thought for this explainer today. We can easily picture 2 lines crossing on a flat piece of paper, or even flat planes intersecting in a 3D room. But the math of matrices, it doesn't stop at 3 dimensions. It works perfectly for 4, 5, or 100 variables. So if these matrices map out real geometry, how do we even begin to visualize planes intersecting infinitely across dimensions that our human eyes can't even perceive? It turns out the numbers hold the secret, even when our own imaginations hit their limit. Thanks so much for exploring the code with me today, and keep looking for those patterns.